a great honor to give a talk for Australian Institute of Physics with many respectable friends, including Murray Bachelor, today's host, and of course, a great tradition starting from Rodney Baxter, and of course, in many other fields. Actually, I have never been to Australia physically, so I should in near future. But for the moment, yeah, it's great to visit at least virtually Australia. Okay, so today I like to talk about the unified framework on conductivities in terms of the response to the time-dependent gauge field. I chose this topic because this is for, as I understand, theoretical physics group. So there will be audience from other fields of physics, like high energy physics and of course condensed matter and maybe nuclear astrophysics and so on. But gauge symmetry and gauge fields are very important concepts across many branches of physics. So I thought this might be of your interest. So yeah, this talk is based on many works in the past and also in recent years. I have listed some of them. Of course, this is not exhaustive list of anything, but one of the pioneering works is by Walter Kohn back in 1964, where he wrote down the famous so-called Kohn formula for Drude weight. And in some sense, my talk is about the extension of his works. And yeah, more recently, I generalized the Kohn formula and the so-called F-sum rule to nonlinear responses in these papers with Haruki Watanabe, who may be in the audience. And also we studied a particular case of single defect in tight binding model in more recent paper with Kazuaki Takasan and Haruki. And actually the study is still ongoing. So my talk is not as complete as I had hoped, but still I hope to give you some ideas and what we understand and also possible future directions. Okay, so yeah, the thing I'm interested is, is conductivity. So yeah, first let's start from the linear response theory. That is, if you apply electric field, then electric field can induce a current. And within linear response theory, the induced current is proportional to the applied electric field. And you can decompose this electric field to frequency and wave number components. And in many applications, we are interested in Q equals 0 component, that is uniform electric field and induced uniform current. So throughout this talk, I focused on this uniform component Q equals 0. Okay. Then still this conductivity has frequency dependence. And yeah, we can consider this conductivity as a function of frequency, which we may call optical frequency, optical conductivity. And this optical conductivity can have a delta function peak at 0 frequency sometimes, and the coefficient is called Drude weight. And basically, this coefficient Drude weight can characterize a transport property of the material. So if D is 0, then basically the system is insulator. But if D is non-zero, this can be only positive. And if D is positive, then this is conductor, and this is discussed in this classic paper by Walter Kohn. And in a realistic system, Drude peak, delta function peak is often broadened by interaction with phonons and so on. But if you consider ideal model, like a tight binding model, Hubbard model, then theoretically we can identify delta function peak. And yeah, this characterizes the so-called perfect conductor. So this is a quantity of great physical interest. Then, so how to formulate this conductivity? So this is one convenient setup. So as often we do in theoretical calculation, we can impose periodic boundary condition in, let's say, x direction. Then if you impose periodic boundary condition, then the system can be regarded as a ring. Then you can introduce a flux, magnetic flux inside this ring. And if you fix this magnetic flux, then these particles or electrons within this system cannot interact with magnetic field directly. So in classical mechanical sense, there should be no effect of this magnetic flux on electrons. But as you know, if you formulate a problem quantum mechanically, then this magnetic flux should be represented by a vector potential. So this magnetic flux still affects the motion of electrons in the system, which is called Aharonov-Bohm effect. So this is quantum mechanical effect. But on the other hand, even in classical mechanics, if you change this magnetic flux as a function of time, then we all know that this time-dependent change of flux induces electric field along this x direction. This can be completely classical effect. And then this electric field can accelerate electrons even within classical mechanics. So this time-dependent effect of time-dependent flux can appear classically or quantum mechanically. And this is actually a convenient setup to consider optical conductivity, that is response of the current to the uniform electric field in x direction. And as I have introduced earlier, usually this Drude weights and so on is discussed in frequency space. So you first define optical conductivity as a function of frequency, then you pick up delta function peak, which is Drude peak. But what I want to argue in this talk is that sometimes it's also useful to consider or formulate a problem in real time. So in real time, the problem looks like this. So you apply a time-dependent electric field in general. Then the current at time t is given like this. This sigma of t is a kind of linear response coefficient, that is time-dependent conductivity, which represents the induced current, how much current is induced by electric field after time delay. So in order to obtain the current at time t, you need to do this integral, that is electric field applied in the past times this response, delayed response of the current with time delay t minus t prime. Then you do this integral. Then you obtain the current at time t. And in this picture, what Drude weight means is that this response coefficient sigma of delay time in the limit of infinite delay. So in perfect conductor, so if there is a dissipation in the system, then if you apply electric fields at some time, then after a very long time, all the effect would disappear. But in perfect conductor, if you apply electric field pulse at, let's say, time 0, then this effect survives even after infinitely long time, at least in ideal limit, theoretically. And how much effect remains after infinitely long time is nothing but the Drude weight. So this is a real-time meaning of the Drude weight. So, for example, if you are interested in the ground state, Drude weight in the ground state, then we can start from the initial state, that is ground state at t equals 0. Then we can switch on infinitesimal constant electric field. But that corresponds to T-linear growth of vector potential in x direction, because electric field is time derivative of vector potential. So in order to represent a constant electric field, we need to increase this vector potential proportional to time. And if you plug in this formula, then under constant electric field, because effect of electric field accumulates in the presence of Drude weight, because the effect of electric field survives even after infinitely long time. The effect accumulates. So under this setting, the current increases proportional to T, and the coefficient includes this Drude weight D. So this is one way to formulate Drude weights in real time. And we can also notice following, that is, what is the current? So the current operator can be defined, or is defined by derivative of the Hamiltonian by vector potential. So this is a standard definition. But if you just take a derivative, then it contains a current operator everywhere. So in order to obtain meaningful quantity, you want to normalize this with 1 over volume. Then this gives you current density. But in our setting, the vector potential is increased proportionally to the time. So this current operator can be related to the time derivative of Hamiltonian. Of course, this is specific to our setting, but we can do this. Then first we consider adiabatic flux insertion, that is increase the vector potential or magnetic flux very slowly over time capital T. Then increase of the energy delta E can be written as a integral of a time derivative of Hamiltonian. But the time derivative of Hamiltonian can be related to the current. So during the adiabatic flux insertion process, the increase in the energy of the system can be related to the integral of the current. And in the adiabatic limit, we can forget about all other contributions than Drude weight, because other contributions die over a long time, but the Drude weight contribution survives after a very long time. So we can plug in this effect of the contribution from the Drude weight to the current. Then we can simply do the integral. So this is a simple high school integral. Then we can relate the energy increase to the Drude weight. So in this way, yeah, we have some identity between ground state energy increase due to adiabatic flux insertion with Drude weight. So I have derived this formula back in 2003, but this is actually not really new, because if you take the limit of small flux, then yeah, this is identical to the famous Kohn's formula for the Drude weight, because Kohn's formula for the Drude weight is nothing but a second order derivative of the ground state energy by vector potential is gives the Drude weight. This famous Kohn formula, which was derived back in 1963 or 4. Okay. So, but as I will show, this real-time formulation can be useful to derive various generalizations of this famous Kohn formula. But before doing so, there is one subtlety I have to mention. That is, there are two different distinct limits to discuss this Drude weight business. So we are usually interested, or at least in condensed matter physics, we are usually interested in so-called thermodynamic limit, that is a limit of infinite system size. And in order to prove the transport property of the bulk, to discuss the conduction property of the bulk, we need to, at least in principle, take the thermodynamic limit first, then consider the adiabatic limit, or equivalently look at the omega equals to 0 limit. Then find the coefficient of delta omega that gives that should give the Drude weight characterizing the bulk property. But if you use Kohn formula, then you first consider finite size system, then consider derivative of energy, but that is ground state energy. So effectively, you are taking adiabatic limit first, and then after that, consider extrapolation to the thermodynamic limit. And these two limits sometimes agree, but not always agree. So that can be a problem. But for the moment, I will mostly discuss the latter limit, the Kohn limit, I will say, the taking adiabatic limit first, then consider extrapolation to the thermodynamic later. But this can cause some problems, so I will come back to the issue later. But for the moment, I will consider Kohn formula limit. Okay. Then, okay, so I will mention some old work of mine, but nonetheless, I thought it might be of some interest, because this is a kind of application of real-time formalism to the issue of conductivity. So as I mentioned, the famous Kohn formula corresponds to inserting infinitesimally small flux. But if we consider a very large system, then we can increase the flux by order 1, in particular to so-called flux quantum. In natural unit, I'm taking the flux quantum is given by 2 pi. So what is flux quantum is that, so if you have Aharonov-Bohm magnetic flux inside a ring, then as I said, as long as phi is constant, static, then it should not have any effect on electrons on the ring. But quantum mechanically, it does. And as you know, the effects of this Aharonov-Bohm flux on electrons on the ring is nothing but the phase difference of electron acquired by going around the system once. So if one electron goes around the system, then you pick up the phase, which is exactly phi in natural unit. So that means that if flux happens to be 2 pi in natural unit, in usual limit it's h over e, then the phase acquired by electron traveling around the system once is exactly 2 pi. And as you know, 2 pi phase is equivalent to 0. So for the electrons living on the ring, they cannot tell whether you have 0 flux or 2 pi flux. So in that sense, this flux 2 pi is special, called magnetic flux quantum. So now I change the flux from 0 to phi 0 gradually. And that is time-dependent process, which produces the electric field. So this electric field does have effect on particles, even classical mechanically. But now I want to formulate the problem in quantum mechanical way. So I start from the initial state, which is a ground state, then increase this Aharonov-Bohm flux from 0 to 2 pi. Then I should reach a final state. So this is adiabatic process. So you should track the eigenstate of the Hamiltonian. But then, so even for 2 pi flux, the Hamiltonian, the final Hamiltonian is different from the original one. because you increased the vector potential from 0 to 2 pi over L. But as I said, the 2 pi flux should be physically equivalent to 0 flux. And this equivalence can be mathematically formulated in terms of gauge transformation, but sort of topologically non-trivial gauge transformation for large gauge transformation. And for lattice model, this large gauge transformation can be explicitly written like this. So basically, this is a phase transformation at each site, but the phase change is proportional to the x coordinate on the system. So you gradually change the phase twist angle along the system linearly in the x coordinate of the system. But the point is that if you go around the system once, x becomes 0, x changes from 0 to Lx. Lx is a system size in x direction. Then phase becomes 2 pi. And then 2 pi phase is equivalent to 0. So this matches very well with periodic boundary condition. And this exactly eliminates the 2 pi flux, which you inserted during this adiabatic process. So mathematically, this can be represented like this. The Hamiltonian with 2 pi flux can be gauge transformed to 0 flux Hamiltonian. So the spectrum of both Hamiltonian are completely identical as physically expected. But the point is that we started from the initial state and end up with some finite state. But in order to get back to the original Hamiltonian, you should do this large gauge transformation. Then the final state after gauge transformation should be given by this. And this may or may not be identical to the starting initial ground state. Okay, so we started from initial ground state, and the final state is given by some time evolution process. But okay, so this is before doing the gauge transformation. But the point is that if my system has a translation invariance, then initial ground state should be eigenstate of the translation operator, which means that this ground state has momentum eigenvalue. Total momentum has some definite value. And because the entire flux insertion process is also translation invariant, because Hamiltonian contains now vector potential, but this Hamiltonian is still translation invariant. So even under this dynamical flux insertion, the momentum eigenvalues cannot change, should not change. So so they have same momentum eigenvalue. But actually, we can find that by doing this large gauge transformation, this large gauge transformation part changes the momentum, because this does not commute with the translation operator on the lattice translation operator to x direction. Because if you sandwich this translation operator by u and u inverse, then because u is given by this, so before and after translation, this x is shifted by 1. So u inverse and u almost cancels, but not exactly, because x is shifted by 1. So we have some remaining term that is exponential of 2 pi I over Lx and the sum over number operators at each site. But the sum of the number operator at each site over entire system is nothing but the total particle number. So the momentum eigenvalue of the final state is changed by this amount by doing the large gauge transformation. Yeah, this is a statement. So we have a momentum shift due to this flux insertion, and the amount of the momentum shift is given by this. So if we consider a two-dimensional system, then the volume of the system is Lx and Ly, and the nu is the particle density, number of particles per unit cell. Then total number of particles, which appears here, is Lx times Ly times nu. but we get a momentum shift 2 pi over Lx times this number. So total momentum shift is 2 pi times system size in y direction times this particle density, which in condensed matter often called filling fraction. So we can choose this Ly freely. So this is a bit tricky part. But if we choose this Ly to be co-prime with this Q, Q is the denominator of this particle density, particle number per unit cell. Then we have a non-trivial momentum shift that is fraction of 2 pi. So if the momentum is shifted by 2 pi times integer, then we cannot distinguish this momentum. But if nu is not integer, some fraction, and if I choose Ly to be co-prime with this denominator Q, then we can say that we got a non-trivial momentum shift. So which tells us that after adiabatic flux insertion and the large gauge transformation, the final state must have different momentum compared to the initial ground state where you started. So this has rather strong physical consequence. That is, you can classify the spectrum of many-body quantum system into two large classes, that is gapless or gapped. And by gap, I mean there's a ground state, the lowest energy eigenstate of the system always. Otherwise, the system is unstable. So we can always assume there is a ground state in the system. Then there are excited states. But often we have a separation between the ground state and the excited states. And this separation is called gap. So in this case, you need a finite, I mean, non-zero energy to excite the system from the ground state. So this is called gap. And in gapless system, the excited states just starts above the ground state, in which case you can excite the system with infinitesimally small energy. And so very roughly speaking, the system is gapped if the system is insulator, because in insulator you can you cannot induce current by very infinitesimally small perturbation. So very generally speaking, you have a gap in insulator, but in case of conductor, you can induce current by infinitesimally small energy. And this kind of discussion can be made precise by present argument. That is, let's assume that we have a gap above ground state. And by now I do this adiabatic flux insertion, starting from zero flux and end up with 2 pi flux, magnetic flux quantum after inserting the magnetic flux quantum. And suppose that the system has fractional filling, that is number of particles per unit cell is fractional, not integer. In that case, if the ground state is unique, then I have just shown that the final state must be different from initial state if the filling fraction, particle density is not integer and fractional. Then that means that the final state must be different from the ground state, means that somehow by adiabatic evolution, this ground state must evolve into one of the ground states. But now, if that happens, then we have non-zero energy increase because they are separated by gap. So because you started from the ground state and end up with one of the excited states if the ground state was unique. And if there is a finite energy increase, non-zero energy increase, we just related energy increase to the Drude weight using the very general argument. So in 2 dimensions, at least, the finite energy increase by going from the ground state to some excited state above the gap, which means that the Drude weight must be non-zero. So the system must be a conductor, at least in standard definition. So yeah, so this is a kind of variation of very well-known Lieb-Schultz-Mattis Theorem, but this is a variation which relates the filling or particle density of the system to the conduction property, the Drude weight of the system. So the final statement I can make is that so I consider very general quantum many by the Hamiltonian periodic lattice, and let's say in 2 dimensions. And if the system has a translation invariance of lattice, then we can always define unit cell. And if the particle number is conserved, then we can always define the filling fraction, that is number of particles by unit cell. And if the number of particles per unit cell filling fraction is fractional, non-integer, then there can be only 2 possibilities. That is, the system is conductor, or the system is insulator. In that case, you must have a degenerate ground state. The reason is that so if the filling is fractional, then I have shown that starting from the ground state, the final state after gauge transformation should be different from the initial state. But if the system was insulator, then D must be 0. Then energy increase must be 0, which means that starting from the ground state, you must end up with a ground state. But the final state must be different from the initial state. Then only possible resolution is that the ground state must be degenerate, which means there must be multiple number of ground state. And you can transition from one ground state to different ground state by this adiabatic flux insertion. That is only possibility for the system to be insulator. So we have choice between these 2, and you can never have insulator with a unique ground state. That is a statement. So this is a very general argument, but this constrains possible quantum phases which arises from whatever model you consider with some fixed particle filling. So, okay, so this is our old story, but I still wanted to introduce because this is one application of adiabatic flux insertion and how you relate the conduction property of the system to this flux insertion, response to the flux insertion. Okay, now I want to switch to the newer development, that is application to nonlinear conductivities. So, well, this is I just want to give a few comments on general motivation. So for a long time, most people have been, especially theorists have been focusing on linear response because linear response is already challenging in many problems. And also I think in many experiments, actually linear response theories work surprisingly well. So why not study linear response first? But of course, there has been studies of nonlinear responses over many years, but especially recently, there is a renewed interest because one reason is that experimental technique progressed, and you can now apply a very strong laser and so on to the system. And then people can measure nonlinear responses in more detail. And one interesting topic, which is not so much directly related to my talk today, but there is something called shift current, which is a second order response, the response of the current to the second order in electric field. And so that is, you apply the electric field, then you can induce the, you can shine the strong light, and you can induce the DC current. And this has a practical potential application to a new kind of photovoltaics. So this has been attracting a lot of attention recently. But I'm not going to discuss any such particular application in this talk, but I have to say that about linear response theory, there has been a lot of theoretical studies over many decades. So we have a lot of systematic understanding. But about nonlinear responses, there are, of course, several works, important works, but the systematic understanding has been largely lacking, I think. So it would be useful to develop some general theory of nonlinear responses. So if I extend the real-time formulation of linear conductance to nonlinear responses, then naturally I can write something like this. That is a current at time t is given by accumulation of effect of electric fields applied in the past, but with some delay time. But now I have nth order, higher order contribution to the electric field. But each electric field can affect the current by different delay time. So the generalized real-time response function has n arguments at nth order, and each argument corresponds to the delay between the applied electric field to current responding at time t. So this is a generalization of nonlinear response conductance in real time to nth order, and eventually you need to sum from a linear response to infinite order, at least in principle. Then similarly to Drude weight for linear response, we can define nonlinear Drude weight by taking the limit of zero delay time like this. And let's call this D of n, Drude weight at nth order. And I had introduced arguments that how you can relate Drude weight to the energy increase of the system. And actually, that argument is not restricted to linear response, because current operator is always given by derivative of Hamiltonian by vector potential. And if you increase vector potential, let's say linearly in time, although in general, we don't have to restrict to linear time evolution, but in the simplest case, I want to increase vector potential linearly in time. And then time derivative of Hamiltonian is proportional to the current. So this relation is valid beyond linear response. So we can just plug in nth order response to this relation and relate the energy increase in n+1 order in vector potential to nth order nonlinear response of the current, and compare the coefficient order by order. Then we find a very simple generalization of Kohn formula at each order of nonlinear response. That is, Drude weight at nth order is nothing but n+1 derivative of ground state energy in the presence of vector potential. And this was presented in my relatively recent paper a few years ago with Haruki Watanabe. And actually, I have to say that in the way I presented, this looks very natural extension of what I did a long time ago. But at first, I didn't notice this, and it was thanks to Haruki who noticed this. Yeah, and now we can. Yeah, so if you restrict this to n equals to 1, this is nothing but the famous Kohn formula. But this is very natural generalization of Kohn formula to nonlinear responses. Okay, so that's one result I wanted to present, the generalization of famous Kohn formula to nonlinear response to all order. And we can also consider opposite limit because Kohn formula corresponds to adiabatic insertion of this Aharonov-Bohm flux. That was because Drude weight is about a very long-term time response of current to the electric field. Basically, we wanted to prove the current after infinitely long time after application of electric field. And a natural setup to pick up this contribution was to insert this magnetic flux infinitely slowly, that is adiabatically. But this flux insertion can be done in other time schedule. So we can also consider sudden insertion. That is, we can still consider this linear increase of vector potential, but over time capital T. And we can consider the limit of this capital T goes to 0, which means that we apply electric field pulse, the constant height, but with the width T, capital T, and consider limit of capital T going to 0 with a fixed area, which means that basically I am discussing delta function like electric field pulse applied at time 0. Okay, then see what happens. So in this limit, so vector potential is basically switched on suddenly. And this is a famous situation of general quantum dynamics, which appears also in undergraduate quantum mechanical textbook. That is, in this kind of limit, so-called sudden approximation becomes exact. That is, Hamiltonian changes at time 0 because you increase or switch on the vector potential suddenly, but the wave function cannot respond. But yeah, again, we are in different gauge. So if you really want to compare the final state with the initial state, you need to apply gauge transformation to eliminate the gauge field. Only after you do that, you can compare the final state with initial state. So it's true that in this limit, sudden approximation becomes exact. So wave function does not change by applying the delta function electric field pulse. But that might sound like there was no effect of electric field on the ground state, but it's not true because wave function did not change, but the Hamiltonian changed. But so if you want to compare final state with initial state, you have to apply large gauge transformation. But the large gauge transformation can be done only if the final magnetic flux is integral multiple of flux quantum. Okay, so there are some subtle issues. But actually, for this purpose, we don't have to do large gauge transformation. But anyway, we can discuss energy gain during this sudden insertion of flux, which is distinguished from adiabatic insertion of flux. But we can use the same technique. But what is different is that the energy increase in this case is just given by this. So this is the expectation value of Hamiltonian with vector potential, magnetic flux, with respect to the original ground state. Or you can say this is the expectation value of original, the same Hamiltonian, with respect to the new time evolved state, well, the final state after doing the large case transformation. But here it's just a simpler to consider. This is just a expectation value of a new Hamiltonian, including the flux with respect to the original ground state, because the original ground state did not evolve by sudden insertion of sudden switching on of vector potential. Then you have to subtract the original ground state energy, which is just a expectation value of original Hamiltonian by original ground state. But you pick up the difference. But this is just a expectation value of difference between new Hamiltonian minus original Hamiltonian with respect to the ground state. And if you are not familiar with so-called Lieb-Schultz-Mattis, you don't have to care. But if you are familiar with so-called Lieb-Schultz-Mattis theorem, then this difference is nothing but famous variational energy increase in original proof of Lieb-Schultz-Mattis theorem, which might be of interest for some of you. Anyway, but then we can compare this energy increase due to sudden flux insertion with this formula. So you plug in the current to this formula, but the current is given by this. So this is nth order response to the electric field. But because now this duration of time, capital T is taken to 0 in this limit. Actually, only this instantaneous response remains. Okay, so maybe this is confusing, but this is a real-time nonlinear response function. So this argument 0 means that 0 delay time. So in this limit, because you switch on the vector potential instantly, after this pulse, you only pick up contribution from nonlinear responses, including linear response, with only 0 delay time. Okay. So there can be effects with time delay, but you are just applying the delta function electric field pulse with infinitesimal widths. So after that, you only pick up contribution from 0 delay time. So if you compare these two sides and compare each order, then you can find the identity between the instantaneous response, that is with 0 delay time, to this quantity. And this right-hand side looks similar to Kohn formula, but this is different. So in Kohn formula, you consider derivative of ground state energy with respect to the vector potential or flux. But this is expectation value of a derivative of Hamiltonian by vector potential with respect to the original ground state. So they are different quantities. And those two differences exactly correspond to two different limits of flux insertion process, adiabatic insertion or sudden insertion. And this left-hand side might look unfamiliar to you. This is just an instantaneous response in real time. But if you go to the frequency representation, then this real-time instantaneous response in real time is given by integral over frequencies. And this this means that you have optical conductivity as a function of frequencies. And if you integrate over all the frequencies, then this integral should be given by this expectation value, which you may calculate more easily. And actually, this is nothing but a generalization of another very famous result, F-sum rule or frequency sum rule for linear response. So if you take n equals 1, this is usual optical conductivity. And if you integrate optical conductivity over entire frequency, then this integral should be given by expectation value like this. And for linear response, this is another very well-known result. But in this way, we can naturally generalize to arbitrary order of nonlinear response. And yeah, using this kind of result, we can also find unexpected symmetries in Drude weight. For example, so dyz of x means that nonlinear Drude weight for current flowing to x direction due to electric field applied in y and z direction. But this quantity is actually symmetric under change of exchanging the indices, which is not obvious by definition, but using this generalized Kohn formula to higher order, this naturally follows. Without using any symmetry of the system. So of course, if the system has spatial symmetry, then this is natural, but without any spatial symmetry of the Hamiltonian, this follows from this one, and so on. Okay, skip this part, and yeah, I just wanted to say that Haruki and his student verified this relation by explicit calculation of tight binding model in 2 dimensions. So it seems to be consistent with our very general formula. And okay, so I'm running out of time, but so I want to mention that yeah, so we, or Haruki and also some other people applied this formulation to calculate nonlinear Drude weight in XXZ chain integrable system, which is for which of course Murray is expert. And then yeah, there's a nice formula based on Lukianov's classic result on this XXZ chain and field theory. From his result, we can give explicit formula for third order Drude weight exactly. It's a nice formula, which also agrees with numerical calculation. But somewhat surprisingly, this quantity diverges for delta, this is anisotropic parameter of XXZ chain below -1/2. So this was not what we expected, but this is exact result which diverges. And later, these people pushed forward this kind of calculation to higher orders. So this is a 5th order Drude weight for XXZ chain. And again, it diverges. Actually, the region of divergence gets bigger and bigger as you go to higher orders, although there are some exceptional points. Yeah, I skipped the detailed calculation, but so we are puzzled by this divergence. So more recently, we studied this even simpler model of just a 1D tight binding model with a single defect, which is exactly solvable model, no interaction. But yeah, this still produces those strange behavior of nonlinear Drude weights. That's our finding. And yeah, I skipped the detail, but this can be formulated in terms of the scattering problem as you did in undergraduate QM, and everything can be worked out exactly. And then, yeah, we found that higher order Drude weight diverges if there's a defect. So this is somewhat surprising, maybe, but everything is exact. So the resolution is actually still ongoing work, but I would mention a few words. That is why this Drude weight diverges even for this almost trivial model of single defect. And I guess even better question, well, even fundamental question is, does a single defect affect the bulk transport property? Because the Drude weight was introduced, I guess, to at least the motivation was to characterize the bulk transport property. But if you think about this, single defect should not affect the bulk transport property, because the bulk property should be independent of boundary condition and so on. And this kind of issue has been discussed in the past by various people. For example, in this paper by Vigo and Shastri in 2008, they discussed the Drude weight in open boundary conditions. And in open boundary condition, naively, the Drude weight should vanish, but the bulk property should be independent of the boundary condition. And they kind of resolve this issue. So the answer is related to the distinction of two limits I had mentioned in the beginning. So in order to prove that bulk property, we should take a thermodynamic limit first, then consider adiabatic limit later. But if you use Kohn formula, then you are naturally taking adiabatic limit first, then consider extrapolation to thermodynamic later. And these two limits sometimes are valid, but not always, in particular for open boundary condition or in the presence of defect. So this difference can be crucial, especially for nonlinear responses. And for the defect model, we did study this issue using the real-time simulation, which is probably difficult for interacting case, but for this defect problem, this is free non-interacting system, so we could do a real-time simulation. This was done by Takasan-san, my collaborator in recent archive paper. So, okay, so, sorry, this is just for two system sizes. And this capital T is the period of flux insertion, the length of the electric field pulse. And I think this red curve is a result of the real-time simulation. And this green wiggly curve is what happens in the adiabatic limit, and or this following the ground state. And if you take the very slow limit, very long schedule, so this is for the width of the electric field pulse to be 10 to 5th times the natural energy scale. Then real-time evolution, of course, almost follows the adiabatic limit. But this adiabatic limit depends on the system size strongly, and also this is kind of unphysical for bulk property, which is affected by defect. But if the width of electric field is sufficiently large, then we don't really follow the adiabatic curve, but we follow something different. And this curve is more representative of bulk property. And actually, for system size 6 and 30, they basically follow similar curve. This is kind of bulk limit. And in this picture, if you go down, this is like taking adiabatic limit. You insert a magnetic flux slower and slower. And to the right, you are going to bigger system. Although I'm here presenting just two system sizes, but going to right corresponds to some limit. So as I discussed, there are two limits. If you go take a adiabatic limit first, then you follow this wiggly curve. Then take time limit, then this adiabatic curve becomes more and more wiggly. But if you want to probe the bulk limit, then you should first fix this T and take the summary limit first. And then after that, you should consider more slower and slower flux insertion. Then you will pick up bulk property of the transport. That's probably the answer, which is not yet quite finished, but that is probably the answer. So, okay, so to summarize my talk, yeah, first I presented some very beautiful framework that is generalization of two very important results for linear conductivity. Both are well known. One is F sample, frequency sample, and the other is Kohn formulas. And I haven't checked every textbook, but usually they are treated separately, I guess. But if you formulate the problem in terms of this flux insertion, response to magnetic flux insertion, then these two seemingly different concepts can be nicely unified as two limits of very similar process, just a flux insertion. So if you insert a flux suddenly, then you pick up instantaneous response, and which is represented by this F sample. And the other extreme is the very slow insertion of flux. And in this case, you reproduce Kohn formula for linear response, but then naturally you can generalize Kohn formula for nonlinear Drude waves. So these are, well, I was personally very happy to see this unification and natural generalization to nonlinear responses. But there is a caveat that is this Kohn formula, you can do some calculation, and sometimes leads to pathological properties like a divergence unrelated to bulk transport. And this is, I think, related to the order of limits. So in Kohn formula, you first take you first take adiabatic limit. But if you want to prove the bulk property, you should take summative limit first, then consider adiabatic limit later. But probably this is more technically challenging. And for linear conductivity, the importance of distinction of these two limits has been discussed in some of the papers, but maybe this distinction was not so much widely appreciated. And going to nonlinear conductivities, this difference between two limits is somehow amplified. That's one of our findings. Yeah. Okay. So yeah, I just wanted to say that in my old paper, I mentioned something like this, but at that point, I didn't work out any complete calculation. So I just claimed that we should take this adiabatic limit after adiabatic limit of flux insertion after taking the summary limit, which I think was a correct statement, but I didn't push this much further at that point. So now, yeah, we have better understanding. And, we can, in some cases, simple cases, do real-time simulation. So, okay, that's it. Yeah, thank you for your attention.
Okay, Masaki, thanks indeed for a very interesting talk. Yeah, there's some very inspiring things there, I think, and particularly back in 2003, where you could sort of look into the sort of, well, you could see what was potentially going to happen. It's very interesting. We do have a couple of questions before I ask a few in the Q&A panel. Can you see that, or should I? Two questions by Vladimir Bajanov.
Okay. Oh, now I can. Sorry, I was not looking at that.
No, that's okay. We can answer them now. I think this relates back to page 9.
Okay.
Your
yeah, sorry.
Presentation.
Maybe I should have answered during talk, but I was
wondering if we should have answered it at that time, but I left it until now. This is to do with the geometry of the.
Yeah. Okay. So, well, yeah. So, to be very formal, we don't have to really think about a ring or this empty space inside the ring. This is just to help visualizing the property. So mathematically speaking, we can just consider this system like on square lattice or cubic lattice or whatever you like, and then impose the periodic boundary condition in one of the direction, x direction, let's say. So this is just like in 2 dimensions square lattice, 3 dimension cubic lattice, and then you impose periodic boundary condition. Then you can introduce vector potential to the link of this square lattice or cubic lattice. And that is mathematically speaking my setup. But in order to visualize the system with periodic boundary condition, you can draw a ring like this, which is kind of fictional. You don't have to do that. But then if you draw this kind of picture, you can insert magnetic flux inside this ring. But in more mathematical formulation, we don't need this empty space or embedding to real space, and just need to increase vector potential defined on the link. And that probably also answers the second question. If we go back to the square lattice or cubic lattice, then square lattice has translation symmetry and cubic lattice has translation symmetry. And even if you introduce vector potential on link, if vector potential on every link is same, uniform vector potential, then you still have translation invariance. Yeah. Sorry, maybe this was rather confusing, but yeah, this was just to help visualizing the Aharonov-Bohm effects. But yeah, I just want to investigate the property of lattice model, like a Hubbard model and so on. Then you can just introduce vector potential. You don't have to embed the system to real space like this. And it's just a response to the vector potential. Still, the large gauge transformation and so on applies. Yeah.
Okay,
That's an answer to Vladimir's question. Okay.
Happy we can answer. But we have a
Michael
question
Hall,
from Michael Hall. Our experiment.
Okay, are experiment possible to physically rule out the divergent? That's an interesting question. So I would say, yeah, so in condensed matter, typical condensed matter experiment, we are interested in bulk properties. But on the other hand, in recent years, there is a great progress in experimental techniques on so-called ultra-cold atoms, and they can set up maybe finite system and even introduce artificial gauge field and so on. And so in that kind of setup, I think this finite size system Kohn formula type response may be more physical in a sense, because I'm not expert on experiments, so I don't know how difficult or realistic is the experiment on cold atom, but in principle, we can consider a collection of finite atoms and introduce artificial gauge field and crank up this gauge field over some time period. Then at least in principle, we can hope to see this Drude type, the Kohn formula type response, completely adiabatic response. But on the other hand, more condensed matter type setting, very large system, then in order to see, well, of course, even in condensed matter system, you can say that every piece of metal, for example, is still finite. There is not really infinite size system. But if you want to probe the really adiabatic Kohn formula type response for large system, like a piece of metal you can see by your naked eye, then the time scale must be enormously large. In that sense, it will be unphysical for bulk property. Yeah, so on the theoretical grounds, we can have some estimate like how slow the process must be to see the adiabatic response characterized by Kohn formula, and for condensed matter, realistic condensed matter system, the time scale is too large to be realistic. That's my general guess. Yeah, but yeah, that's important and interesting question. I still we are trying to work out.
Yes, that's really fantastic. Yeah, so I did have a question about the divergence, but you've already answered that. So, and you've already started to do some concrete calculations on a number of many body interacting models. So I'm sure there's more there as well. So really, as there are no other questions in the Q&A panel, I think we'll stop there. And thanks again, Masaki, for a really fantastic talk. Thanks a lot.
Thank you.